Question 7 from the 2025 Higher Physics Examination from the SQA. A student sets up an experiment in a darkened room to investigate the relationship between irradiance I and the distance d from a point source of light. The apparatus is used as shown. You can see we've got a small lamp, we have a meter stick, a light sensor and a light meter. The distance between the lamp and the light sensor is measured with a meter stick. The irradiance is measured with a light meter. And the results obtained in a table shown below. We can see we've got a distance from the light sensor to the small lamp, 0.200, 0.400, and the corresponding irradiance from the light meter, measured from the light meter. So part A for 1 mark says what is meant by the term irradiance, and that can be summed up by this little picture here. The irradiance is really equal to the power of the radiation arriving on a certain area of surface. We say that the irradiance is equal to the power divided by the area. And the power, remember, is a measure of the amount of energy per second. So really what we're saying is irradiance is the amount of energy per second arriving in a unit area. And we can work that out by saying irradiance equals the power of the radiation divided by the area. And that's your definition of irradiance. Now part B is asking us, it says use all the data in the relationship between irradiance I and distance d to see if we can establish a relationship between irradiance I and distance d. Now when you see this coming into play, the first thing you should be thinking of is the inverse square law. So it's something to do with the square of the distance. So your first strategy is to draw out the table and then add in an extra row, all to do with the distance squared. So we take the distance and we square it and we get the following row in the table. You can see that 0.200 squared is 0.04, 0.400 squared is 0.16, and 0.600 squared is 0.36, and 0.800 is 12.4. And that's going to give you the value of the distances squared. Now the next thing I'm going to try and do is add this one here. I'm going to put in I times d squared to make it easy for myself. But remember, the clue is to do with the inverse square law. It's something to do with square of the distance. So I'm putting down I times d squared. And if I go through my calculator, I end up with this series of numbers here. I can see I've got I times d squared is going to be 7.936, 7.936, 7.92, 7.936. So to one decimal place, we can see that I times d squared is really a constant number. So we can put it down as follows. We can say that I d squared, I times d squared, is going to equal to a constant number. We'll call that constant number k. In this case, ID squared is going to become equal to 7.9 to one decimal place. So that's the relationship then. It's asking you the relationship between the irradiance and the distance. Therefore we can write the following. We can say that the irradiance I is going to equal to 7.9, the constant number, all divided by d squared. Which means if we know the distance from the light source and square it and divide it into 7.9, we will get the irradiance of that particular source of radiation. Question 7 continued, part C. Other than repeating each measurement and calculating the mean, suggest 2 improvements that could be made to the student's experimental procedure. Well, we know the experiment is taking place in the dark, in the very darkest room possible, with all the blinds shut in a dark room. But we have to make sure that we don't include any unwanted reflections. So that's the first one then, is to make sure you remove all the unwanted reflections. And to do that, you can put a black coating or a black mat on the table so that none of the reflections off the table will be arriving at the light sensor, and the light sensor is picking up just that little part of area of the radiated light. One other thing is that the inverse square law only really works for point sources of light, and we can't really get point sources of light in the lab, so what we have to do is use the smallest filament bulb possible. So a small, bright filament bulb, very, very small indeed. You cannot use an LED because an LED only throws light off in one direction, a small kind of like area of direction. So you have to make sure you've got a smallest lamp possible, smallest filament possible, that's going to radiate light in all possible directions. So that's a possible 2 there for you. The other one from the experiment is when you're actually taking the measurements of the experiment, you are really just measuring from the light sensor to the edge of the bulb, the actual glass of the bulb. So possibly another way you could do that is take into account the radius of the bulb and subtract that from, or add that on to your readings in order to give you the true distance from the light sensor to the filament itself. And that would be take into account the distance to the filament. So that's your 3 possible answers to improve the experimental procedure, but you only have to have 2 for that. Now part D says a second student carries out an experiment using a laser instead of a lamp. Part I says the laser beam is initially shone onto a light sensor from a distance of 0.20 meters. The beam produces a uniformly lit circle of diameter 1.0 times 10 to minus 3 meters on the light sensor. And the irradiance of the circle of light is found to be 1.51 times 10 to the power 3 watts per meter square. And for 4 marks we have to determine the power of the laser beam. Well, we know the equation we're going to use for this. The equation is going to be that the irradiance of any radiation source is going to be equal to the power falling upon a particular area. So irradiance is power over area. And we can rearrange that to give us what the power is. The power is actually equal to the irradiance and multiplied by the area. So that's just got our working equation there. Now we know the irradiance, that's this value down here, 1.51 times 10 to the power 3. All we have to do is work out the area of the actual beam. So if we take a kind of snapshot of the beam or see it on the wall, we can see it's going to be like that. There's the red area of the laser beam. It's really exaggerated for clarity here. Now we know that the diameter of it is double the radius, so the radius of the beam is going to be a half the diameter, because we know that the area of a circle is pi r squared, so we can work out what the area is. The area of that is going to be pi times r squared, which is going to be equal to simply pi times, if we look at the distance, the diameter is going to be 1.00 times 10 minus 3, so therefore the radius is going to be 0.5 times 10 to the minus 3. So we've got pi multiplied by the radius squared, and the radius squared is going to be 0.50, half the diameter, times 10 to minus 3, and remember we have got to square that. So we've now got the area, we know the irradiance, it's just a matter of plugging all the sort of numbers in to give your answer. And we do the following. We have the power of the laser beam. I'll do this up here for you. The power has got to be equal to the irradiance times the area, and we know what the irradiance is because it tells you that it's going to be 1.51 times 10 to the power 3, and it's going to be watts per meter squared, and we have to multiply that by the area, which we've got over here, and it's going to be pi times 0.50 times 10 to the minus 3, and don't forget to square the radius because the area is pi r squared. So if you do that on your calculator, you end up with a value of 1.19 times 10 to the minus 3 watts, and we can show off and say that's going to be 1.19 milliwatts. That's going to be the power of the laser beam. Question 7D continued, part 2. The student moves the laser to a distance of 0.40 meters from the sensor. The reading on the light meter does not change. Suggest why the reading does not change. Well, this is peculiarity due to a laser beam. You see, if we shine a laser beam onto a screen or onto a sensor, the diameter of the beam is very, very small indeed. This is actually exaggerated. It's a very small diameter beam. Now, because the laser has got a concentrated light, it's very coherent light. It means that if you move the laser further away from the actual screen, it's not going to make any difference to the diameter of the beam. So if I take that laser and move it further away from the screen to over this position, the diameter of the laser beam falling onto the sensor or the screen doesn't change at all. It's only if it's going really quite a big distance away you'll get a little bit what we call beam divergence. So the answer to that one mark is when you move the laser further away, because of the nature of the laser light, it's very coherent, and therefore if you move the laser beam away from the screen, the diameter of the beam landing on the screen doesn't appreciably change. And if the diameter doesn't change, the radius doesn't change, and therefore the irradiance, which we know is going to be equal to the radiance, is going to be power over the area. If the area doesn't change and the power remains the same, then the irradiance is going to still be the same. And that's why you get the reading on the light meter not changing.